Hello everyone, engineering statistics and linear algebra. All these concepts are discussed. Today we do discuss bivariate expectations, uncorrelated, orthogonal, independent, correlated random variables x and y. After a complete discussion, we will solve some of the problems. Bivariate expectations. Before discussing bivariate expectations, we do highlight single random variable expectations. A mean of a random variable. It is also called as a first moment about the origin. It can be defined as x into fx of x into dx. So fx of x, it is a single random variable probability density function. So a mean of a random variable x is denoted with three different notations. Next is what? A mean of a square of a random variable x. It is also called as a second moment about the origin. That can be denoted with the different notations, and it can be defined as x square into single random variable probability density functions. It is integrated over minus infinity to plus infinity with respect to x. Variance, also called as the second moment about the mean. It can be denoted as a variance of x or sigma square of x, and it can be defined as expectations of, in the bracket, x minus mu x. What is mu x here? Mu x is a mean of a random variable x. A standard deviations, it is nothing but a square root of variance. And consider the transformation here. Y is one random variable, x is one more, y is defined in terms of x here. Apply expectations on both sides. Expectation of y can also be denoted as mu of y. Expectation of ax plus b. Use a linearity property of expectations. Apply e inside the bracket. E into f of a of x plus a into b. A is a constant, take it outside. B is a constant, expectation of b itself is b. So that mu of y, e of x can be written as mu of x. This relation is very important in future, so that keep this point. If x and y random variables are defined with this relation, then mean of x and y can be correlated using this formula. So with this basics, let us define expectations of bivariate random variables. A mean of a bivariate random variable, it can be denoted with three different notations, and it can be defined as a double integration with respect to x and y. So g of xy, it is an arbitrary function defined in terms of only x and y, and it is called as a bivariate probability density functions. So this is called as a mean of a bivariate random variable. Using this, we can calculate e of x. If g of xy is defined only in terms of x, let us consider one example here. If g of xy happens to be a function of only one random variable, say x, g of x is a function of two variables. Instead of two variable, let us define g of xy only in terms of x. At that time, xy bar becomes x bar, mu of xy becomes only mu of x, e of g of x comma y becomes only e of gx. So g of xy is defined only in terms of x, so that take it outside. Then f of xy, x comma y dy into dx, it is called as a bivariate probability density functions. And we know the formula. Integration of bivariate random variable with respect to y, that can be replaced as fx of x, that is already discussed. So using bivariate random variable, using bivariate probability density functions, if arbitrary function is defined only in terms of x, then we can calculate expectation of a single random variable x. Next concept is correlation. Actually, the correlation is a product of two random variables x and y, and it is denoted as E of xy, and it is mathematically defined as x into y bivariate probability density functions. They are integrated with respect to x and y over the limits minus infinity to plus infinity. Actually, the expectation is conceptually same as averaging. Expectation, correlation, and averaging. So generally they are one another same. Averaging is adding all the numbers, dividing a number of how many number of variables are there. If that is divided, then we will get average of a number. So this is a general formula for getting an average of a given different numbers. So this correlation can be of three types. It can be positive, negative, or it is uncorrelated. Uh, The use of correlation is it gives the relationship between two random variables x and y. When correlation is positive, then this is the example for a positive correlation. We can take any random variable. A relationship between x and y is always positive here. Already we have said that it is a product of x and y. We can take any point. X is positive, y is positive, so that product of these two is positive here. We can take this point. Y is negative, x is negative. Product of those two is positive here. And a correlation can be negative, and average always it is less than 0. Example for this is this graph. You can take any graph here, any point here on the graph. So y is positive, x is negative. As a result, product of those two is negative here. And uncorrelated, and the correlation is 0 here. Example for this uncorrelated correlation is this graph. So these 2 points and these 2 points are equal and opposite, so that they are cancelled, and these two are equal and opposite, they are cancelled, and so on. As a result, so correlation can be a positive, a negative, and uncorrelated. All right, what is a covariance here? Covariance can be defined only if the mean of a two random variable is non-zero, and generally covariance can be denoted as covariance of x and y, and it is defined as using this equation. So mu of x is a mean of a random variable x, mean of a random variable y. X is a random variable, y is a one more random variable. Covariance of x and y, if the mean of those two is not equals to 0, then it can be defined using this equation. Let us apply a linearity property into this equation. Multiply inside the bracket x into x, xy, mu into x into y, minus mu y into x, and mu x into mu y. Later, apply expectation inside the bracket. Expectation of xy, mu x is a constant, take it outside. Next, mu y is a constant here, take it outside. Expectation of constant is constant itself. So that E of y, expectation of y, it can also be denoted as mu of y. Expectation of x can also be denoted as mu of x. After simplification, one standard relations between correlation, covariance, and mean of a random variables. It is the one good relations between all these parameters. Covariance of xy equals to correlations between x and y minus mean of x into mean of y. All right. And from this equation, we can conclude here as if any one of the mean of a random variable is 0, then we can say that covariance of x and y equals to correlation of x and y. That is defined here. A mean of any one of bivariate to be 0, then we can say that covariance and correlations, they are one and the same. All right. Keeping this point in our mind, let us define what do you mean by uncorrelated x and y and what do you mean by independence. Uncorrelated xy can be defined if the covariance is 0. In the equation, if covariance is equals to 0, that gives a product of mean of x and y that will be equals to correlation of x and y. We can observe here, if covariance of x and y is 0, then this term will be equals to this one. That is defined here. That is nothing but uncorrelated x and y. If you want to say that random variables x and y are uncorrelated, then covariance of x and y should be 0. If covariance equals to 0, then correlation of xy equals to a product of mean of x and y. Alright, what do you mean by orthogonality of x and y? If correlation of x and y is 0, then what could be the value of covariance of xy? That will be equals to negative of product of mean of x and y. When do you say that two random variables x and y, they are orthogonal each other? The condition is correlation should be equals to 0. Apply that concept to this formula. As a result, covariance of xy equals to minus of mean of x into mean of y. So when do you say that x and y are correlated? Only if covariance of x and y should be equals to 0. To say that x and y are orthogonal each other, then correlation of xy should be equals to 0. Alright. Next we do discuss independence of x and y. So independence of xy can be defined using this formula here. Expectation of x to the power n into y to the power m, if they are independent, then it can be written as a product. So apply expectations formula here. So g of xy is defined in terms of x and y, x to the power n and y to the power m, and fx of x and fy of y, it is integrated with respect to dx and dy. Alright, why it is bivariate random variable is defined in terms of product of single random variable? It is a property of a bivariate random variable. If you want to say that a bivariate probability density function is to be independent, then that should be equals to product of individual probability density functions. Actually here we do write here f of xy comma xy, that is written in terms of a product of two single random variables. That is written only if they are independent. Using that concept, a bivariate PDF is replaced as a product of two single random variable probability density functions here. Separate the integration. So it can be written as expectation of x to the power n, expectation of y to the power m. So if x and y are independent each other, then expectation of product of x to the power n into y to the power m can be written as expectation of x to the n into expectation of y to the m. And we have discussed uncorrelated random variable x and y only speak to the case when n is equals to m is equals to 1. That is what we have defined uncorrelated xy. If covariance equals to 0, then we have said that correlations of xy equals to mu of x and mu of y. This mu of x, can it be written as e of x? Mu of y, can it be written as e of y? These two are one another same. The difference is, in this case, n and m are equals to 1. Based on this concept, we do conclude one thing is, independence applies uncorrelation, but reverse is not true. You can say that if power n is equals to m is equals to 1, you can say that it is independent as well as uncorrelated, but reverse is not true. Reverse is not true. If power is 2, m is equals to n is equals to 2, if they are independent means then you cannot say that they are uncorrelated with each other. If they are uncorrelated each other, then definitely they are independent. All right. What do you mean by correlated x and y? This is the concept where we can define a correlated efficiency. It is denoted as rho into x into y, and it is defined as a ratio of covariance of xy divided by standard deviation of x and standard deviation of y. Consider x and y with the following relation. Two random variables x and y are considered here. Y is defined in terms of x. Apply expectation on both sides. E of y, it is also called as a mu of y. A is a constant taken outside. Expectation of b is b itself. This equation can also be written as a into mu of x plus b. And we know the definition of a covariance, that is already discussed. In the place of y, let us replace ax plus b, that is written here, minus of. In the place of a mean of y, let us replace this equation. So minus of a of mu of x minus b, because of this minus sign. Alright, plus and minus b are cancelled each other. After simplification, a is a constant, so taken outside, and a is a constant, to take it outside. A minus b into a minus b whole square. So it can also be written as, it is also be written as variance of x. That is the definition of variance of x here. The variance of x can be denoted as e x minus mu x whole square. So this is nothing but variance of x. A covariance of x and y, if x and y are defined with this relation, then that can be written as a into a variance of x. And one more thing is, it is a concept of a first module here. Let us we glance once again. Let us take a relationship between x and y, apply expectation on both sides. A is a constant, out, take it outside. So expectation of B is B only. As a result, mu of y equals to A into mu of x plus B. So this E of x can also be written as mu of x. Alright, we know the definition of a variance. Variance of y is defined here. That can be written as E of y minus mu y whole square. And replace this y in terms of x. That is written here. Y in terms of x, it is written, and mean in terms of mean of x, that is substituted here. Alright, because of this minus sign, these two are minus, plus b minus b, they are cancelled. As a result, ax minus a mu x are remaining. A is a constant, take it outside. It is a square, so that a square is taken outside. Then it can be written as variance of x because of the definition of a variance. I can observe here, both are one another same. This expression and these expressions are one another same. So it can be written as a square into a variance of x. To take square root on both sides, mu of y plus or minus square root of a square, it can be a into mu of x. So same thing is written here. These two are one another same. It is a concept of a first module. That is just we have revised here. And what is correlated efficiency here? It is the ratio of covariance of xy into mu of x into mu of y. Covariance of xy, that is calculated here, a into variance of x divided by, what is variance of x? What is variance of x? Let us write as it is. What is variance of y? Variance of y, that is calculated here, that is nothing but a into sigma of x, that is written here. So a will be cancelled, so sigma square divided by sigma of x into sigma of x, they will be cancelled. As a result, correlated efficiency will be always plus or minus 1. So it varies from minus 1 to plus 1, so not more than that. To prove that correlated efficiency equals to plus or minus 1, these are the steps should be followed by you people. Alright, let us summarize all these things. So a bivariate random variable, expectations of a bivariate random variable, that is first thing is a mean of a bivariate random variable, that is defined here. And correlations between x and y, it is actually the product of those two. So this correlation may be positive, a negative, or uncorrelated. So keep the point in your mind, correlation of xy is nothing but a product of x and y. And next is covariance. Covariance will come to the picture only when a mean of random variables x and y should be 0. And a definition of a covariance of xy is defined using this formula. So generally covariance of xy is defined using this formula. After simplification, we do come with one standard equation here. And one conclusion we can make from this equation is, if any one of the mean of a random variable 0, then you can say that covariance and correlations are one another same. Alright. When x and y are uncorrelated, that means When covariance equals to 0, then we can say that correlations equals to a product of mean of x and y. Alright, when correlation of xy is 0, then we can say that covariance of x and y equals to a minus mean of x into mean of y. When do you say that x and y are independent? If this is the case. If this is the case, then you can say that x and y are independent in nature. Then a correlated efficiency that can be defined as covariance of xy divided by sigma of x and sigma of y. It is nothing but standard deviation of x and the standard deviation of y. Always it varies from plus or minus 1. Keeping all those points in our mind, let us solve one problem here. F of fx of x, fy of y, and a bivariate probability density functions are given here, where x and y's are varying from 0 to 1. Calculate expectation of x, expectation of y, and expectation of xy. That is what it is, a correlation. Here the product is used here, so that it is also called as a correlation of x and y. All right, we know e of x, expectation of x, it is nothing but a mean of x using formula x into fx of x into dx, where x is varying from 0 to 1. In that range, what is fx of x? It is 1 here. Replace it by 1. What is integration of x? X square by 2. Apply the limits, equals to 1 by 2. Similarly, expectation of y. So a PDF of y is given here. It is 1, where x and y's are varying from 0 to 1. Alright. Integration of y is what? Y square by 2. Limits are varying from 0 to 1. After simplification, result is 1 by 2 here. Alright. What is correlation of xy, or expectation of x and y, or mean of x and y? So x into y, a bivariate PDF integrated with respect to x and y. Bivariate PDF for the range 0 to 1 is 1. It is given here, given data. As a result, separate the integration here, x into integration of x into dx over the limit 0 and 1. Next, integration of y into dy over the range 0 to 1. It can be replaced by 1 by 2. It can be replaced by 1 by 2. As a result, 1 by 4. So you can say here e of xy equals to mu of x and mu of y, that is equals to 1 by 4. Then what could be the conclusion here? Covariance of x and y are 0 here. Using this, we can see here, if covariance of x and y's are 0, then we can say that a mean of a random variables x and y equals to a correlation of x and y. So after calculation, we have come to know that expectation of xy equals to a product of mean of two random variables x and y, that is equals to 1 by 4 here. So what could be the conclusion after the simplification? The covariance of xy, that is covariance efficiency, is 0 in this case. Alright, here a mu of x, mean of x is given, it is variance is given to, mean of y is given, variance of y is given, and covariance efficiency, that is 0.5 is given here. They have asked us to calculate covariance xy and correlation of xy. Alright, we know this formula, all are given here. A covariance of xy is asked here. So substitute here, covariance of xy is equals to, so it is a standard deviation, but variance is given here. So square root of variance is a standard deviation that can be calculated here. As a result, a covariance of xy is 1.4142. Now, using this formula, then correlation of xy can be calculated here. So correlation of xy equals to covariance of xy plus a product of mean of xy. It is already calculated here, 1.4142 plus mu x is 1, mu I is 3. 1 into 3 is 3, 3 plus 1.4142, that gives 4.4142. All right, let us consider one more problem here. Mean and variance of random variables are -2 and 3. Mean and variance of y are 3 and 5. A covariance of xy is minus zero point -0.8. What are the correlation efficient and a correlation of xy? Based on the problem, let us write a given data here. Mean and variance of random variables are -2 and 3. That is written here. It is mu x and variance. Similarly, mean and variance of y, they are given here. Covariance is given here, and they have asked a correlation efficient and a correlation of E and E of xy. Using this formula, the first correlation efficiency can be calculated here. And using this formula, we can calculate the correlations between x and y. Alright, they are simple problems. So the mean and variance of, let us consider next problem. The mean and variance of random variables are -2 and -3. Mean and variance of y's are 3 and 5. The correlations efficiency is 0.7. What are covariance and correlations? Alright, write down the given parameters. Use this formula. Let us calculate a covariance. All are given data here. So it is given as a 0.7. It is given as a square root of 2, square root of 3. It is given as a square root of 5. So after simplification, it is 2.711. Alright, they have asked us to calculate correlation of xy. Using this formula, it can be calculated. Covariance is already calculated here, 2.711. Mu of x, mu of y. So -2 and 3, -6 plus 2.711. That gives -3.2889. I think these are simple formulas. So let us take this as assignment problem. Mean and variance of x are -2 and -3. Mean and variance of y are 3 and 5. Correlation is given here, -8.7. What is covariance of xy and correlation efficiency xy? So take this as an assignment. In the next video, we will solve some more problems on these concepts, and if you have any doubts, so feel free to ask me. So like, share, comment on the video, and don't forget to subscribe the channel. We see in the next video. Thank you.